Hi, I'm Mr. Parker and this is question 6 on the OCR Mechanics 1 paper from June 2009. For more questions on this exam paper, click the link here or check in the video description. Question 6. A block B of weight 10 newtons is projected down a line of greatest slope of a plane inclined at an angle of 20 degrees to the horizontal. B travels down the plane at constant speed. In part 1a, we need to find the components perpendicular and parallel to the plane of the contact force between B and the plane. As always, let's start by drawing a diagram. So this part here where it says line of greatest slope of the plane, all that really means is it's going to slide down the slope. And we've got a weight of 10 newtons. Be careful here not to put 10g, it's telling us the weight here, it's not telling us the mass. Let's add the other forces. We've got the normal contact force, which we'll call R, which is perpendicular to the slope. And we've also got a frictional force stopping it going down the slope. Now because we know the block is moving, we can call that limiting friction. And that is all the forces acting on the block. We'll begin by finding the component perpendicular to the slope. So resolving perpendicular into the slope, we're going to have a component of this 10 Newton force. And the angle here between the force and the direction we want to go in is 20 degrees. You could actually show that using a bit of basic trigonometry with right angle triangles if you wanted to. So we get 10 cosine 20 degrees. Coming out of the slope, we've got the normal contact force. Because I've chosen this component to be positive and the normal contact force is in the opposite direction, we'll put this as minus R. As there's no acceleration into or out of the slope, we can say that equals 0. So we get R equals 10 cos 20. And if we do that, we get 9.40 to 3 significant figures. Resolving parallel to the slope, we've got a component of this 10 Newton force. And if in the perpendicular direction it was 10 cos 20, that means in the parallel direction we are going to get the component of the weight as 10 sine 20 degrees. The only other force that has any impact parallel to the slope is limiting friction, and because we've decided the weight going down the slope is positive, we're going to put minus F lim. It says the block is going down the slope at constant speed, and that means that the acceleration is 0, so we can say 10 sine 20 minus F lim equals 0. That means F lim will be 10 sine 20 degrees, which gives us 3.42 to 3 significant figures. Part B says, hence show that the coefficient of friction is 0.364, correct to 3 significant figures. Hopefully you're aware that limiting friction is defined to be the coefficient of friction mu multiplied by the normal contact force R. If we rearrange this, we get mu equals F lim divided by R. It's important here that you use the exact values for these calculations. Don't use your rounded answers from part 1. So I'm going to do 10 sine 20 divided by 10 cos 20. Now I could just put that into my calculator, but 10 divided by 10 is 1, and sine 20 divided by cos 20 is just tan 20. And in fact, it's always the case, if you have a block on a slope with no other forces other than the weight and friction acting on it, that the coefficient of friction is tan of the angle here. And as required, we get 0.364 if we round to 3 significant figures. In part 2, it says B is in limiting equilibrium when acted on by a force of T newtons directed towards the plane at an angle of 45 degrees to a line of greatest slope. Given that the frictional force on B acts down the plane, find T. First of all, let's put in this frictional force. So it's going down the plane, and because it's in limiting equilibrium, we can call that force F lim. In the previous part, we also had 2 other forces. We had the weight of the block, which was 10 newtons, and we had the normal contact force, which we'll call R. Note that this time the normal contact force and the limiting friction will be different to last time because of this force T. So we'll begin by resolving forces perpendicular to the slope. As before, we've got a component of this 10 Newton force coming into the slope, and that's going to be 10 cos 20. we've also got a component of this T newtons force coming into the slope. And if the angle between the force and the slope is 45 degrees, if we were calculating in the direction parallel to the slope, we would do T cos 45. That means in the other direction perpendicular to that, we are going to do T sine 45. As it's going into the slope, it will be positive. And we've also got the normal contact force, which is coming out of the slope, so we'll put minus R for that. Limiting friction isn't involved in this part because that's parallel to the slope, and it equals 0 because there's no acceleration. So we can rearrange that to get R equals 10 cos 20 plus T sine 45. We can't go any further with this because we've got two unknowns, R and T. So next we're going to resolve parallel to. This time the component of the 10 Newton force down the slope will be 10 sine 20. The T Newton force is acting up the slope, and as we've taken this to be positive, this is going to be negative, and the angle between the force and the slope is 45 degrees, so we get minus T cos 45 degrees. Notice here how we had cos 20 for perpendicular, that means we've got sine 20 in the parallel, and we had sine 45 from perpendicular, so we've got cos 45 for parallel. We've also got limiting friction acting down the slope, so we get plus F lim. And again, there's no acceleration, so that equals 0. Following on from this, we're going to use the fact that F lim equals mu r. And in the previous question, we showed that mu was 0.364 to three significant figures, but I'm going to use tan 20 because that's more accurate. Now, although F lim and r have changed in the problem that we're doing, the coefficient of friction, mu, is just to do with the properties of the block and the slope, so that actually doesn't change if we change the forces. So we know that mu equals tan 20. So our next step will be to replace limiting friction with mu multiplied by r, which we worked out here. So all I'm going to do is substitute in mu r for F lim. Be careful when you're substituting in here to put this expression for r inside a bracket, because you're multiplying tan 20 by all of this. Next I'm going to expand out this bracket here. The next step I'm going to do isn't strictly necessary, but it does help us to simplify things down. Here I've got tan 20 cos 20. And I know that I can rewrite tan 20 as sine 20 over cos 20. And then we multiply that by cos 20. And hopefully you can see the cos 20 on the top and the bottom will cancel out and leave us with just sine 20. So here where I've got tan 20 cos 20, I'm just going to replace that by sine 20. In order to solve this equation, I'm going to get all the terms containing t on the same side. So I'm going to take these two terms over to the right hand side. At the same time, I'm going to do 10 sine 20 add 10 sine 20 and simplify that to 20 sine 20. Moving this over to the other side makes it positive, so I get t cos 45. And moving this over to the other side makes it negative, so I get minus t tan 20 degrees sine 45 degrees. Now that my terms involving t are on the same side, I can factorise. Finally, all I need to do is divide through by this bracket here, and I get t equals 20 sine 20 divided by cos 45 minus tan 20 sine 45. And that gives me 15.2 to three significant figures.